All right, welcome back. This is part 2 of module 1 lecture. Oops, excuse me. Okay, so what we're going to kind of hit on here in this lecture is some basic cellular functions here. So the theme of physiology is this term called homeostasis. It sounds like a complicated word, but it's actually a pretty simple concept. So homeostasis is defined as the body's ability to maintain stable internal conditions, no matter what's going on the outside. And that's just a mechanism to promote survival. So for example, it's freezing outside, right? So let's just say that it's like negative 30 degrees Fahrenheit. And your body internally is still 98.6. How does that happen? Homeostasis. So because it's so cold outside, your body is going through mechanisms internally to maintain that 98.6 degree temperature, no matter what's going on out here. Okay. And we do that by, for example, with temperature regulation, shivering, making those muscles contract, which generates heat. Goosebumps, which are going to be like constriction of the skin surface. Your blood vessels are going to constrict as well to conserve heat and things like that. And we'll get into more of that. But homeostasis is the body's ability to maintain internal conditions, no matter what's going on the outside. And it does this by 3 steps. So the first step is a receptor detects a change in the environment. So let's just say you walk outside and it's really cold and your hands get cold, right? So you have thermoreceptors or temperature receptors in your fingers, right, that are going to send a message through your nervous system up to your brain. And that message is, hey, it's really cold. We need to do something to conserve our body heat, right? Then your control center, which is your brain, is going to make a decision, and it's going to send a message out to your body to perform different tasks to maintain the body heat inside. And what it's going to do is send a message back out. And what happens then is going to be the effector. So your brain might tell your skeletal muscles to contract and shiver, right? Your brain might tell your blood vessels to constrict and hang on to that body heat. And then it just repeats. So this is a fluctuating process. It's always going on 24/7. And there's 2 types of different feedback that can happen to send that message to the brain and out. Negative feedback, positive feedback. So we're going to review those. Now, if we're talking about negative feedback is defined as the reversal of a trend back to a set point. And if you think about a set point, that's your normal. Okay, so for example, let's just say your normal body temperature is 98.6. Well, during the day, it fluctuates. Like in the middle of the night, your body temperature actually drops pretty significantly. And in the afternoon, everybody's a little higher at like 99 or 100 degrees normally. Okay, so that set point is 98.6, but we have this constant higher, raising and lowering of that body temperature all the time. Now, let's just say, for example, that your body temperature raises too high. And let's just say this is a fever, for example. Let's say you get a fever. So your temperature is too high. It's above 98.6. This is how we're going to work through this. That's the stimulus. That's something that sends a message to a receptor and says, hey, trigger it, right? The receptors are going to be your thermoreceptors. So you have thermoreceptors that are detecting body temperature all throughout your body. Let's just say this one's in your skin, for example. So you have a thermoreceptor that detects that, hey, it's too hot. So we're going to send a message up to the brain. Okay. And the brain here is your control center. And specifically your hypothalamus is responsible for body temperature regulation. And it's going to detect that we're too high above that 98.6. And it's going to signal, excuse me, the other organs of the body to do something about it to try and cool you off. So we send a message back out, and this is going to be the effect. So your blood vessels are going to dilate. Now, when your blood vessels inside your body dilate, they release heat to the outside environment. And if we release heat to the outside environment, well, that's great because the inside environment then will cool down, right? Also sweating. So sweating is perspiration. It's creating liquid, right, on your skin surface. And when that liquid evaporates, that causes a natural cooling sensation and can then also cool down the body. Okay. And then hopefully with those things in place, now our body temperature can come back down to the normal 98.6. What about the opposite? So let's just say that we're too cold. Let's say we go outside in Nebraska in the middle of the winter and you are freezing because we have like -18 with like a -45 wind chill, right? I'm sure some of you out there are from much colder places, but that's just what I have to complain about. So let's just say that it gets very cold. Your stimulus is just that, right? The temperature drops. And again, your thermoreceptors are detecting that drop in temperature saying, hey, it's really cold. We're going to tell the brain. The hypothalamus does a few things, right? So let's just talk about this short loop first. So the short loop is going to be that your blood vessels are going to constrict, which I said when they expand, that releases heat to the environment. Well, we don't want to do that, right? We want to hang on to that heat as much as we can. So your blood vessels are actually going to constrict. And then your sweat glands, we're not going to use them, right? So they're going to become inactive. And then hopefully you return to your set point that way. Now, if it doesn't, now we can start doing shivering motions and things like that. So your muscles are typically voluntary, right? They're typically under voluntary control, but your body does have a mechanism in place that can make them constrict involuntarily. And that's for a survival mechanism. So if we have shivering, we're so cold, we can actually have a mechanism in place that causes our muscles to contract involuntarily, and muscle contraction generates heat in the form of energy. And so that can also help our body temperature come back up. That's negative feedback. So notice the theme in those two things was we're returning back to a set point, right? Now, positive feedback is a little bit different. Positive feedback is like we want to keep going with something until an end point or a solution happens. So, for example, if the temperature example was positive, our body temperature would just keep lowering and lowering and lowering and lowering. And we just keep going until, I don't know, we get hypothermia and die. I'm not sure. That's not ideal, right? With positive feedback, something's going and going and going and going to achieve a positive solution. So the best example of this is childbirth. So, for example, we're going to start, let's see here. Once a woman becomes so pregnant, right? Her stretch receptors in her, her stretch receptors in her uterus are going to sense that change. Now, when they get so stretched, now they're going to send a signal to the uterus to contract, start squeezing that muscle. And that muscle squeezing in the uterus will push the fetus down towards the birth canal. And that increases, it only increases, right? Contractions only get bigger and stronger. And as that head moves towards the cervix is going to stretch further. Okay. And as that cervix stretches further, again, we repeat the cycle. Those contractions get more intense, more intense, more intense. Now, if this was negative feedback, those contractions, we would want to stop them, right? And that's not ideal because if we're having a baby, you want to get that baby out, right? So this is an example of positive feedback. So continuing a trend in this constant circle until an end point, not a set point, an end point is reached. And the end point here is going to be the birth of that baby. Another example would be blood clotting. If you've ever heard of that one. So your platelets and factors in your bloodstream work around the clock to get that platelet plug and that bleeding stopped. If we did that in a negative feedback fashion, we'd start bleeding again, right? But you never start, well, I shouldn't say you never. You usually don't start to bleed again after your blood clotting mechanism has happened. So stopping something to an endpoint to achieve an endpoint. Okay. So just know, and this is something that's going to be really important this term in this class, homeostasis is a multi-organ affair, and it is because it involves all kinds, right? So for example, let's just say that we have nutrients, salts, and water coming in our digestive tract because we've eaten something, drank water, all of that kind of thing, right? We've ingested things. Well, your cardiovascular uses those things. Your respiratory system uses those things. Your kidneys use those things. And all of these things, three things together, actually can go back and regulate how your digestive system works as well. And we're going to talk a lot about this in a lot of examples every single week, because the point of physiology, especially with these specific organ systems, is going to be integration. How do these things all work together? And just for example, a really great example would be your cardiovascular system and your urinary system working together to maintain blood pressure. Those things work very, very closely together. Very different places of the body, right? But they work very closely together to maintain blood pressure. So just keep in mind that this is a very integrative process. I'm going to kind of switch gears a little bit, and I'm just hitting on all of those learning objectives in Module 1. The most important inorganic substance that we have in our body is water. It's going to be kind of the theme of the semester or the term here. Water is H2O, 2 hydrogen ions, 1 oxygen ion, right? And water makes up 2/3 of our human body weight, including like our bloodstream. Okay, so our blood is actually mostly water, and then cells and proteins and other things make up a very small percentage of our blood. Urine, also comprised of mainly water. All right, so the majority of our body fluids are made of water. So water is very, very important. We're going to talk a lot about water balance. Another thing I need to hit on is the definitions of solvent, solute, and solution. So this is kind of some chemistry thrown in here. So a solvent is a substance in which other substances are dissolved. So a lot of times your solvent is going to be water, right? If we're talking about the blood, all of our cells and our ions and things like that are in this liquid called water or plasma. The solute is going to be what's dissolved in the solvent. So solutes, for example, we've got a lot of sodium in our bloodstream, right? And sodium is a very small ion in a pool of water-based plasma. And then the solution is just going to be your solvent plus your solute together. And so a good example is salt water. So let's just say that salt water is your solution. So what would be your solute and what would be your solvent? So your solute is what you're dissolving, or the particles, right? And so that's going to be your solute, and then your solvent, you're in water, right? Salt in the water. This is an example of a sugar cube, which you can also do the same thing, right? So here's your sugar cube. That's your solute. You're dissolving that in water, which is your solvent. And then sugar water would be your solution after it's dissolved. I like to hit on this one because we're going to talk a lot about solutes, especially when we get to fluid maintenance with the cardiovascular system, mostly urinary system. Lots of terminology with solutes. So that's what's dissolved in something, right? And in this case, in the human body, a lot of times that solvent is going to be water. So then what's an electrolyte? So an electrolyte is a compound that ionizes in water. So something that breaks apart in water. But the unique thing here is that those compounds that it breaks into are actually electrically charged. So your sodium, your potassium, your calcium, your chloride, all of those things have a charge, if you remember from general chemistry. So an example, table salt, which is NaCl, sodium chloride. Okay, dissolve that in water, and that NaCl, that salt's going to dissolve. You're not going to see it anymore, right? It has dissolved into sodium ions and chloride ions. Well, sodium has a positive 1 charge and chloride has a negative 1 charge. And those are electrically charged particles. And what you'll find out in the body, if you remember from muscle contraction, is that sodium is very important to adjust the action potential of a contraction. And so with the heart, especially in this chapter, we're going to talk a lot about that with sodium and potassium and their electrical capabilities, being able to stimulate a muscle contraction. There are 3 types of electrolytes: acid, bases, and salts. So acids, in terms of what makes them, like their properties, like what makes it an acid, we're talking about hydrogen ions. And so free hydrogen ions, think about hydrogen plus being acidic. And if you can remember that hydrogen is acidic, that's going to help you with everything else. So an acid releases hydrogen ions into the environment, so it's acidic. Bases bind those up and take them out of the environment. And a salt is going to be the reaction product of an acid plus a base to generate a neutral salt. Okay. So, for example, just keep in mind again that it's all about the hydrogen, right? Hydrogen ions. H2O, water, can dissociate into hydrogen ions and hydroxide ions, but water is considered neutral. However, if we talk about sodium hydroxide, for example, sodium and hydroxide ions, okay, so hydroxide can then combine with hydrogen ions to form water if it wanted to. So let's just say that we put sodium hydroxide in water. Let's say that that's a solute and our water is a solvent. What could happen is that sodium hydroxide is going to dissociate into sodium and hydroxide. And then the water molecules, the hydrogen ions from the water, are going to combine with that hydroxide to form water again. But essentially what we call this is a base. Now, OH negative is a base. Okay, so if hydrogen ions are acidic, OH negative has to be a base. And why? Because it can combine with hydrogen ions to form water. Okay, now, on the other hand, right, hydrogen can combine with OH to form water as well. Like if you flip it around, do the reverse. So hydrogen ions are going to be an acid. Acids plus base equals water plus electrolytes. So for example, if we have hydrochloric acid, okay, HCl, plus sodium hydroxide, so this is an acid, very strong acid, plus a very strong base. When those 2 things combine, they form water and salt, literally, NaCl and salt and water. So a very strong acid plus a very strong base equals water plus salts. So ultimately, your body is made up of lots of acids and bases. And a lot of those things are carried through the bloodstream as salts or ions or salts that are dissociated. Like, so we might have salt in our body, but it's dissociated as Na plus and Cl minus. And that way that our body doesn't, the pH doesn't fluctuate too much. Now, I'm going to keep boring you with some chemistry here. If we're talking about fluid chemistry, we're talking about pH, for example, and pH is the measurement of hydrogen ions in the bloodstream. So I said hydrogen is acidic, right? So if hydrogen is acidic, then we are paying attention to how many of those we have in fluid and then measuring the pH off of that. So the more hydrogen ions you have, which are free hydrogen, right? The more acidic you are and the lower the pH you are. So pH scales from 1 to 14. 7 is neutral, lower than 7 is acidic, higher than 7 is basic. 1 step in pH, so like from 1 to 2, is actually a 10-fold in the concentration of hydrogen ions that you have. And so your hydrogen ions are exponentially greater as you move down the pH scale as more acidic. Now, our blood has a pH, right? Our urine has a pH. All those fluids have a pH, but how do we keep those things in check, right? We don't want our urine or our blood to get too acidic or too basic, because then that's going to throw off our homeostasis. So we have buffers. And buffers are systems that resist pH change. And your body has actually a lot of natural buffers that help this happen. That's why our blood doesn't get too acidic. And these are going to combine. They can either combine with excess hydrogen or release hydrogen, depending on what the environment is. So let's just say, for example, that your blood is too acidic. If your blood is too acidic, you have buffers that are going to bind up that hydrogen, take it out of the extracellular environment and bind it up so that it's no longer causing a lowered pH. And then vice versa. Let's just say that your blood gets too basic, right? So these buffers have bound up all these hydrogen ions. They can release them into the environment. And if they release them, right, if they're free again, it's going to lower your pH a little bit, just back to normal. And a very common system that we have is the buffer system in your body called the carbonic acid bicarb buffer system. We're going to talk a lot about this when we get to respiratory system. But ultimately what you have, we know that we breathe out CO2, right? We breathe out carbon dioxide. But if you hang on to too much carbon dioxide, let's just say that you hold your breath. Okay, if you hold your breath, you're not breathing out enough carbon dioxide, right? What that carbon dioxide does, it's in your bloodstream. It can combine with the water that's in your bloodstream and form something called carbonic acid. Okay, carbonic acid dissociates into free hydrogen ions and bicarbonate. Okay, so the more CO2 you have in your blood, the more you're hanging on to, right? The more acidic your bloodstream is, or the more acidic your body is. And this bicarb is a natural buffer. We have some of this bicarb in our body at all times. It is there to bind up these hydrogen ions or release them. Okay, depending on what's going on with our pH. And we're going to talk more about that when we get to the respiratory system. All right, I'm going to stop there for this session, and I'm going to let you take a quick break. And when we come back, we will get going with the last lecture.